In the depths of space lies mysterious regions, and maybe those very regions inhabit mysterious creatures. Maybe you've heard of black holes, those mysterious regions in the universe where gravity is so strong that nothing at all, can escape. But have you ever stopped to think about what's really at the heart of every galaxy? Because what is coming next is something that no one has heard of. Monsters hiding at the center of almost every galaxy in the universe. But we are not talking about some giant space creature lurking in the shadows, ready to devour everything in sight. What we are really talking about is something much stranger. The supermassive black hole. These black holes are like invisible giants at the core of galaxies, so massive and powerful that they shape the very fabric of the galaxies they live in. But how did they get there? And what do they actually do? What exactly is a supermassive black hole? A supermassive black hole is one of the most mysterious objects in space, and for good reason. And these objects are unlike anything we encounter here on Earth. To understand a supermassive black hole, we need to first understand what a black hole is in general. A black hole, in its simplest form, is a region in space where the gravitational pull is so strong that not even light can escape. The reason we call them black holes is because they don't emit any light, making them invisible to our eyes. But how do they get so powerful? Well, a black hole's strength comes from its mass and its incredibly dense concentration. Think of it like squeezing all the mass of a star into an area that's so small that it creates a gravitational force far beyond anything we can imagine. This is where things start to get interesting. A black hole doesn't just suck in matter, it distorts space-time itself. Space and time behave differently near a black hole, warping in ways that are still difficult for us to fully comprehend. Now, a supermassive black hole takes this idea to an extreme. These behemoths are the heavyweights of the black hole family, with masses ranging from millions to billions of times the mass of our Sun. But they're not just larger versions of stellar black holes. Their formation, behavior, and role in the universe are incredibly different. To put it simply, supermassive black holes are like cosmic giants at the center of galaxies. They have so much mass and gravitational pull that they influence the very structure of their galaxy. In fact, the more astronomers study them, the more we realize that they are intimately tied to the history, evolution, and behavior of the galaxies they inhabit. But how and when did they become so massive? And why are they always at the centers of galaxies? To answer that, we need to dive deeper into their origins and the role they play in the universe. How do these monsters form? While there are a number of competing theories, one thing is clear. These black holes didn't just pop up overnight. They've had billions of years to grow and evolve. But how did they get to such mind-boggling sizes? One popular theory about the formation of supermassive black holes is that they began as small black holes in the early universe. After the Big Bang, the universe was filled with gas and dust. In the first few 100 million years, this gas began to clump together, forming the earliest stars and galaxies. But some regions of gas might have been so dense that they collapsed into proto-black holes, the seeds of what would become supermassive black holes. These early black holes could have had masses anywhere from a few hundred to a few thousand times that of the Sun. These proto-black holes would have formed in the very dense regions of space, where gas was clumped together and gravity was incredibly strong. Once these small black holes were formed, they could have started to grow by pulling in more matter. This very process, known as accretion, involves gas and dust from the surrounding region falling into the black hole, causing it to grow larger and larger over time. But accretion alone might not explain how these black holes grew to become the supermassive giants we see today. Another possibility is that these early black holes grew by merging with other black holes. In the chaotic environment of the early universe, galaxies were constantly colliding and merging, and as they did, their central black holes would have merged too, forming a larger supermassive black hole. But we don't talk without proofs, we can't. This idea of black hole mergers is supported by evidence from the LIGO detector, which has detected gravitational waves from the collision of smaller black holes. If small black holes could merge into bigger ones, it's not hard to imagine that over billions of years, these black hole mergers could lead to the creation of the massive black holes we observe at the centers of galaxies today. As galaxies continued to evolve, the central black holes would have continued to grow. But here's where things get really interesting. These supermassive black holes didn't just sit quietly at the center of their galaxies. They had a direct impact on their surroundings, influencing the entire galaxy. This feedback loop, where the black hole shapes its galaxy and vice versa, played a key role in the growth of both the black hole and the galaxy itself. For instance, the intense radiation released by an active black hole can heat up surrounding gas and prevent it from collapsing into new stars. This means that the black hole can literally control the rate of star formation in its galaxy. We might as well call the black hole the boss of the galaxy, deciding how fast it will grow. In fact, this process, known as AGN feedback, is thought to play a role in the way galaxies evolve, regulating how many stars are formed and how the gas in the galaxy behaves. These feedback loops can also explain why some supermassive black holes become so active at times, emitting massive amounts of radiation and even powerful jets of particles. This kind of activity happens when the black hole is feeding, while pulling in large amounts of gas from its surrounding environment. As the gas falls in, it forms an accretion disk around the black hole, heating up to millions of degrees and emitting bright radiation. Some black holes go through long periods of intense activity, followed by quieter phases, and this can have a massive impact on their host galaxies. But while we have some ideas about how supermassive black holes form and grow, there are still many unanswered questions. Why are supermassive black holes always in the center of galaxies? When we look at the universe, we notice a curious pattern. Almost every large galaxy we observe seems to have a supermassive black hole at its center, which might make one wonder, why is that? Why aren't black holes scattered randomly throughout galaxies? For that, we need to take a deeper dive into the very nature of galaxies themselves and understand why the center is such a unique and important place. At the heart of this mystery is gravity, the fundamental force that governs how everything moves in the universe. In any galaxy, gravity pulls everything toward the center. This is why stars, gas, and dust are all concentrated around a galactic center. Think of it like a bustling city where everything is moving toward the central hub. In the same way, the material that makes up a galaxy is attracted toward its center, where the most gravitational influence lies. In fact, the center of a galaxy is the place where the densest and most massive objects are found. As you move outward from the center, the density of stars and gas drops off. The same way that a town center has the highest population density, the galactic center is the densest place in the galaxy. This makes it an ideal environment for the formation of a supermassive black hole. The concentration of mass in the center naturally leads to the formation of a gravitational well, and over time, a black hole can form in that well, pulling more and more material in, becoming larger and more powerful. Beyond just gravity, there's another key reason why black holes are found at the centers of galaxies: gas and dust. In a galaxy, gas and dust are constantly in motion, and much of this material is funneled toward the center by the galaxy's gravitational pull. As gas gets closer to the black hole, it begins to swirl around it, forming what's known as an accretion disk. An accretion disk is like a glowing, spinning ring of material that forms as matter spirals inwards towards the black hole. As this material gets closer to the event horizon, the point of no return for a black hole, it gets heated up to incredible temperatures, emitting light, X-rays, and other radiation. This process of gas falling into a black hole and emitting energy is one of the reasons black holes can be detected, even though they don't emit light directly. So, the center of the galaxy is the natural place for this process to occur. It's where the most gas, dust, and stars are, and this abundance of material makes the formation of a supermassive black hole much more likely. The role of galaxy collisions and mergers. But since there's another factor that's often overlooked, like the galactic mergers, galaxies don't just sit still in the universe. Over billions of years, galaxies collide, interact, and sometimes merge into one larger galaxy. When galaxies merge, their central black holes, if they each had one, begin to interact, eventually merging into an even larger black hole. These galaxy mergers play a key role in the growth of supermassive black holes. When two galaxies collide, their central black holes are drawn toward each other, and over time, they spiral inward and eventually merge. This process can result in the creation of a black hole that's far more massive than its predecessors. It's like two giants coming together to form an even greater giant. And the merging black holes can grow significantly in mass as they accumulate more material from their surrounding galaxies. So, not only do supermassive black holes form naturally at the centers of galaxies, but they also grow through these cosmic collisions. In fact, astronomers believe that most large galaxies, including our own Milky Way, probably formed their central black holes this way, the galactic core. There are things that we didn't know, and one of them is that the center of any galaxy is an extreme environment, full of chaotic interactions. For example, stars in the central regions of galaxies move at much higher speeds than those in the outer parts. This high-speed movement, combined with the intense gravitational forces at play, makes the center of the galaxy the perfect breeding ground for black holes. In this environment, the conditions are just right for matter to be compressed, energy to be released, and black holes to form and grow. It's also worth noting that the center of the galaxy is the place where the most energy is concentrated. In galaxies with an active supermassive black hole, the area around the black hole can become an active galactic nucleus, AGN, one of the brightest objects in the entire universe. In these cases, the supermassive black hole is consuming large amounts of gas, and the radiation from this process outshines the rest of the galaxy. AGNs are so powerful that they can sometimes be visible from millions of light-years away, and they serve as a clear indicator that a supermassive black hole is at work at the galaxy's center. What happens to a galaxy when it has a supermassive black hole? Once a supermassive black hole takes up residence at the center of a galaxy, it doesn't just sit there, quietly minding its own business. These black holes have a massive influence on everything around them, from the stars that orbit them to the gas clouds that swirl nearby. The first and most obvious way a supermassive black hole affects its galaxy is through gravity. A black hole's gravity is incredibly strong, and as such, it dominates the motion of stars, gas, and dust near the center of the galaxy. In fact, by studying how stars move around a black hole, astronomers can calculate its mass with incredible precision. The stars near the black hole move at high speeds, which suggests that a massive object, our supermassive black hole, is pulling them toward it. But this isn't just limited to stars. The black hole's gravity affects the galaxy's entire structure. The orbital dynamics of stars and gas in the galaxy are directly influenced by the central black hole. As material falls toward the black hole, it can change the shape and behavior of the entire galaxy over time. How the black hole can control star formation. One of the most intriguing effects of a supermassive black hole is how it can regulate the formation of new stars. In some galaxies, the intense radiation and energy released by an active black hole can actually heat up the surrounding gas, preventing it from condensing and forming new stars. This process is known as feedback, and it can slow down or even halt the birth of new stars in a galaxy. In an active galactic nucleus, AGN, where the black hole is actively consuming matter, the energy released can be so powerful that it blows gas out of the galaxy. This is called a galactic wind. As a result, the galaxy may stop producing new stars, and over time, the galaxy will evolve into what we call a red and dead galaxy, one that has exhausted its supply of gas and can no longer form new stars. But not all galaxies experience this kind of feedback. In some galaxies, the black hole is dormant, and the gas surrounding it continues to condense and form new stars. This means that the presence of a supermassive black hole can have a great effect on the entire star formation process in the galaxy. The feedback loop, black hole, and galaxy growth. The relationship between a supermassive black hole and its galaxy is not one-sided. There's a feedback loop at play, where the black hole shapes the galaxy and the galaxy shapes the black hole in return. When a black hole consumes a lot of gas, it grows larger, and the energy it emits can influence the surrounding galaxy. This feedback mechanism can lead to a balancing act between black hole growth and galaxy evolution. In some cases, the black hole may grow so large that it becomes the dominant force in the galaxy, controlling its growth and evolution. In other cases, the galaxy itself might limit the black hole's growth by preventing more material from falling in. But the balance between the two remains unknown, and astronomers are busy researching and trying to figure out the whys. Active galaxies and quasars. But what we know so far is that when a black hole is feeding, it becomes an incredibly bright source of energy. In some cases, the energy emitted by the black hole can be so intense that it outshines the entire galaxy. These super bright objects are called quasars. A quasar is a type of active galactic nucleus where the central black hole is consuming material at an extraordinary rate, creating a blazing beacon of radiation. Quasars are among the most powerful and energetic objects in the universe, and they can be observed from billions of light-years away. In fact, the light from quasars has helped astronomers study the distant universe and understand how galaxies and black holes have evolved over time. The gravitational influence of the black hole. Now that we know why supermassive black holes tend to form at the centers of galaxies, let's explore what happens when they take up residence. What effect do these giant black holes have on the galaxies they inhabit? At first glance, you might think that a black hole's only effect is to consume everything around it: stars, gas, planets, and even light. But in reality, the gravitational influence of a supermassive black hole is far more subtle, and it goes beyond just pulling objects into its abyss. In fact, the gravitational force of a black hole dominates the motion of everything in its vicinity. The stars closest to the black hole move at incredibly high speeds, their orbits being bent and stretched by its immense gravity. This movement tells astronomers something important. By watching how these stars move, we can measure the mass of the black hole. The faster the stars are moving, the more massive the object at the center must be. For instance, in the case of our own Milky Way galaxy, the black hole at the center, Sagittarius A star, has been measured to have a mass around 4 million times that of our Sun. We can infer this by tracking the orbits of stars near the black hole. They zip around it at speeds of up to 27 million kilometers per hour, a clear indication of just how powerful its gravitational pull is. But it's not just the stars that feel the black hole's influence. The surrounding gas and dust are pulled toward the center as well, forming an accretion disk. This disk is a rotating collection of material spiraling toward the black hole, and it can get incredibly hot. So hot that it emits powerful radiation detectable by telescopes. This radiation can affect the entire galaxy, both in terms of its structure and its star formation. Active galactic nuclei and quasars. We have by far heard the term active galactic nucleus. But what we don't know yet is what this region actually is and what it holds. An AGN is a highly energetic and compact area at the center of a galaxy, powered by a supermassive black hole actively feeding on surrounding material. The energy generated by an AGN can be so intense that it outshines the entire galaxy. When the black hole at the center of a galaxy is feeding actively, it creates an incredibly bright emission of radiation. The process of matter falling into the black hole, called accretion, heats up the material as it spirals inward, causing it to emit radiation across the electromagnetic spectrum. This radiation is so bright that it can outshine the combined light of all the stars in the galaxy. A galaxy with an especially powerful AGN is known as a quasar. Quasars are among the most energetic objects in the universe. They can emit more light than an entire galaxy of stars. In fact, the light from quasars can travel billions of light years, making them visible from vast distances. Quasars were more common in the early universe, and studying them helps astronomers understand the conditions that existed when galaxies and black holes were first forming. While quasars are fascinating objects in their own right, they also have a significant impact on their host galaxies. The energy output from a quasar can blow away surrounding gas, preventing it from collapsing and forming new stars. This process, called AGN feedback, can shut down star formation in the galaxy, effectively aging the galaxy. So, the energy produced by supermassive black holes does more than just light up the night sky. It can change the course of the galaxy's evolution by regulating star formation and controlling the flow of gas. But here's where it gets really interesting. That energy doesn't just shine outward, it pushes back. And that's when the black hole stops being a spectacle and starts acting like a regulator. The cosmic regulator. It can be thought of as a giant cosmic thermostat, where the black hole is the one setting the temperature. As we just discussed, the feedback from the supermassive black hole can heat up the surrounding gas, causing it to be blown away, much like a strong wind scattering dust. This feedback process helps regulate how much gas can be funneled into the black hole, which in turn controls how active the black hole is. The energy released by a black hole's accretion disk can push gas away from the center of the galaxy, preventing it from being consumed. If enough gas is pushed out, the black hole will have less material to feed on, and it will become less active. This is one of the ways that supermassive black holes self-regulate their growth. But the feedback isn't always a one-way street. The presence of a black hole can also influence the galaxy's structure over time. In some cases, the activity of the black hole can cause ripples that spread out through the galaxy, affecting how stars move and interact with each other. Some galaxies have relativistic jets that shoot out from the black hole's poles, carrying energy and matter to far-off regions. These jets can stretch across millions of light years, and their energy can affect star formation in distant parts of the galaxy. What happens when a black hole is dormant? Yet interestingly, not every supermassive black hole is constantly active. Many black holes are dormant, meaning they're not feeding on anything and aren't emitting vast amounts of energy. In these cases, the black hole is still a dominant force in the galaxy, but it's not actively affecting its environment in the same way an AGN or quasar would. Even dormant black holes still play an important role in the dynamics of their galaxy. The gravitational influence they exert on stars and gas in the center of the galaxy is significant, and they continue to regulate the movement of objects around them. They might not be active at the moment, but they remain a powerful force nonetheless. The role of supermassive black holes in the evolution of galaxies. But there's a broader picture, a larger truth we might want to deny. A question like, how do supermassive black holes influence the evolution of their galaxies over time? It's clear that black holes have a deep impact on their immediate surroundings, but they also shape the larger-scale development of their galaxies. One of the most fascinating discoveries in recent years is that supermassive black holes and galaxies seem to evolve together. In fact, the mass of a supermassive black hole is often related to the properties of its host galaxy. This relationship suggests that the formation and growth of supermassive black holes and the galaxies that host them are interconnected. For example, studies have found a correlation between the mass of a supermassive black hole and the velocity dispersion of stars in the galaxy's bulge. This suggests that the formation of the galaxy and the growth of the black hole are linked in some way. Astronomers believe that as galaxies evolve, they go through periods of intense star formation, followed by periods where star formation slows down or even stops. Supermassive black holes play a key role in this process by regulating star formation. When the black hole is active, it can blow away gas, preventing it from collapsing and forming new stars. As a result, the galaxy may enter a phase where it stops producing new stars and starts to age, becoming a red and dead galaxy. In galaxies with dormant black holes, star formation can continue at a more normal rate, allowing the galaxy to keep growing and evolving over time. This gives us a fascinating view of how the life cycle of a galaxy is linked to the activity of its central black hole. The feedback loop between black holes and their host galaxies. The interplay between supermassive black holes and galaxies is not just a one-time event. It's an ongoing, dynamic relationship. We talked earlier about the feedback mechanism, where the energy from a black hole's accretion disk can regulate star formation. But there's a deeper level to this feedback, the black hole galaxy feedback loop. In galaxies where the black hole is particularly active, the radiation and jets produced by the black hole can affect the galaxy's gas, slowing down or halting the collapse of gas clouds that would otherwise form stars. This feedback process can eventually lead to a mature galaxy with fewer stars being formed. In this sense, the black hole is directly influencing the future growth of the galaxy itself. Over billions of years, this process of feedback can shape a galaxy in dramatic ways. It can determine how many stars the galaxy will form, how quickly the galaxy will evolve, and what the ultimate fate of the galaxy will be. If the black hole is particularly active, it could lead to a galaxy that becomes old and quiescent. If the black hole is dormant, the galaxy might continue to produce stars for billions of years, creating a young, vibrant galaxy that will evolve for eons to come. The ultimate fate of supermassive black holes and their galaxies. But in the distant future, what will happen to these supermassive black holes and their galaxies? It's a fascinating question that astronomers are still trying to answer. As galaxies continue to evolve, they will eventually merge with other galaxies, and their black holes will likely merge as well, creating even more massive, supermassive black holes. The future of these black holes will depend on how much gas they can continue to consume and how active they remain. Over trillions of years, as galaxies continue to collide and merge, supermassive black holes will likely play a central role in shaping the fate of the universe. How do we detect them? When we think about black holes, one of the first things that might come to mind is their invisibility. After all, if not even light can escape, how could we possibly detect something that's effectively hidden from view? And yet, despite their elusive nature, astronomers have developed several methods for detecting the presence of supermassive black holes across the universe. Observing stellar orbits, the first clues. Let's begin with one of the most groundbreaking techniques used to detect black holes: watching the stars. When a supermassive black hole sits at the center of a galaxy, it exerts a strong gravitational pull on nearby stars. The stars in the galaxy's core are pulled towards the black hole, and as they orbit it, their movements give us important clues about its presence. By studying the orbits of stars near the galaxy's center, astronomers can measure how fast these stars are moving, and, from this, calculate the mass of the black hole. The faster the star's orbit, the more mass the central object must have. Since we can't see the black hole directly, the next best thing is to track these stars as they swing around the invisible object at the galaxy's center. In fact, observations of stars orbiting the black hole at the center of our own Milky Way, Sagittarius A star, were key in confirming the black hole's mass, which is around 4 million times the mass of the Sun. The power of X-rays. Hot matter and accretion disks. Another crucial way we detect black holes is by looking at X-rays. So when gas and dust are drawn into a black hole, they don't just vanish. Instead, as material spirals inward, it forms an accretion disk, a hot, glowing ring of gas. This disk gets incredibly hot, up to millions of degrees, and as it heats up, it emits powerful X-rays that we can detect with space-based telescopes. A luminous accretion disk is like a cosmic spotlight. As the gas moves closer to the event horizon, it accelerates, and frictional forces heat the gas to temperatures that produce X-rays. By detecting these X-rays, we can observe black holes that are actively feeding on nearby material. This is one of the reasons quasars, which are supermassive black holes feeding at full throttle, are so bright. Their accretion disks radiate vast amounts of energy, often outshining the entire galaxy. Gravitational lensing, the warping of light. One of the more fascinating ways we can detect black holes, especially supermassive ones, is through gravitational lensing. The surprising part, as per Einstein's theory of general relativity, is that a black hole's massive gravity bends light that passes near it. This effect is called gravitational lensing, and it happens when the black hole warps space and time so much that light from objects behind it gets distorted. When light from a distant star or galaxy passes near a black hole, it can be bent into a ring or arc, which is known as an Einstein ring. This phenomenon allows us to spot black holes by the way they distort light in the background. Scientists have used this effect to discover black holes that would otherwise be invisible, hiding in the center of galaxies. The Event Horizon Telescope. What has now been ongoing for decades is that astronomers could only detect black holes indirectly, through their gravitational influence or radiation. But in 2019, the world got its first glimpse of a black hole, thanks to the Event Horizon Telescope, EHT. Using a network of radio telescopes spread across the globe, the EHT captured the first image of a black hole at the center of the galaxy M87. This was a monumental breakthrough, as it was the first time scientists had ever directly visualized the shadow of a black hole. The image showed a glowing ring of gas around a dark central region. This dark spot is the black hole's event horizon, the point of no return. Although we can't see the black hole itself, this image of the shadow was a huge step in confirming their existence and understanding their properties. Gravitational waves. Perhaps one of the most exciting ways to detect black holes is through gravitational waves. These are ripples in the fabric of space-time caused by massive objects like black holes colliding. When two black holes merge, they send out gravitational waves that travel through space at the speed of light, stretching and compressing space-time as they go. In 2015, the LIGO, Laser Interferometer Gravitational Wave Observatory, made the first detection of gravitational waves, confirming a prediction made by Einstein nearly a century earlier. Since then, LIGO and other detectors have observed several black hole mergers, including the collision of two supermassive black holes. These discoveries have opened an entirely new way of studying the universe, allowing us to hear black holes rather than just see them. Supermassive black holes and the early universe. As we now embark deeper into the history of the universe, one of the most tantalizing questions scientists have been asking is, how did supermassive black holes form so early? The mystery of their formation. Supermassive black holes are found at the centers of most large galaxies, but some of them are already in place just a few 100 million years after the Big Bang, a time when the universe was still very young. One possible explanation is that massive clouds of gas in the early universe collapsed into black holes directly, bypassing the normal stellar collapse process. These direct collapse black holes could have formed much faster than the traditional black holes formed from dying stars. Once these early black holes formed, they could have grown rapidly by accumulating gas and merging with other black holes. Astronomers are still investigating the exact mechanisms behind this rapid formation, and the James Webb Space Telescope, JWST, which launched in December 2021, is expected to provide new insights into how these supermassive black holes emerged so soon after the Big Bang. So we need to keep a close watch. Supermassive black holes and quasars, the brightest beacons in the universe. In the early universe, some of these supermassive black holes powered the brightest objects in the universe, quasars. Quasars are the highly luminous active galactic nuclei that we see from billions of light-years away. Their brightness comes from the incredible amounts of energy produced when matter falls into a supermassive black hole, forming an accretion disk that heats up and radiates light. Quasars are so bright that they can outshine all the stars in their host galaxy. In fact, they were some of the first objects discovered in distant galaxies, helping astronomers study the early universe. Observing these ancient quasars allows us to understand what the universe looked like just a few 100 million years after the Big Bang, giving us a unique glimpse into its infancy. The role of supermassive black holes in galaxy formation. As we continue to investigate the early universe, we begin to see how supermassive black holes might have played a key role in galaxy formation. It's now believed that black holes and galaxies are co-evolving, meaning that the growth of supermassive black holes could have influenced the formation and evolution of the galaxies around them. For example, the energy released by quasars may have regulated star formation in the galaxies that host these black holes. When black holes are active, they can blow away gas, preventing new stars from forming. This process likely played a significant role in the early evolution of galaxies, shaping the structure of the universe we see today. The ultimate fate of supermassive black holes. As powerful as they are, supermassive black holes aren't eternal. In the distant future, after galaxies have merged and star formation has slowed to a halt, what will happen to these cosmic giants? What's their ultimate fate? Black hole mergers, the beginning of the end. As the universe continues to expand and galaxies collide, many supermassive black holes will eventually merge. This process will produce some of the most energetic events in the universe, releasing massive amounts of energy in the form of gravitational waves. These black hole mergers will play a critical role in the final stages of galaxy evolution. The collision of supermassive black holes could also lead to the formation of even bigger black holes. These newly formed giants would be the last remnants of the old galaxies, the survivors of a universe that has evolved and merged over billions of years. The fate of black hole. The ultimate fate of supermassive black holes could be even more bizarre. According to the theory of Hawking radiation, proposed by physicist Stephen Hawking in 1974, black holes can slowly lose mass and energy over time through the emission of radiation. This radiation, called Hawking radiation, would cause black holes to lose their mass, gradually shrinking them until they eventually evaporate completely. However, this process would take an extraordinarily long time, far longer than the current age of the universe. For supermassive black holes, it would take billions of years for Hawking radiation to cause any noticeable effects. So, while it's a fascinating possibility, we won't be seeing black holes disappear anytime soon. The end of the universe. In the very distant future, after supermassive black holes have merged and stars have exhausted their fuel, the universe will eventually reach a state of cosmic darkness. As galaxies lose their gas and their black holes evaporate, the universe may become a cold, dark place where no new stars can form. This could be the final chapter for supermassive black holes and the ultimate fate of the universe itself. The mysterious role of supermassive black holes in galaxy mergers and cosmic evolution. When we look out into the cosmos, we're not just seeing a collection of stars and galaxies, we're seeing a dynamic and evolving universe where galaxies merge, collide, and evolve in a cosmic dance. Central to this dance are the supermassive black holes that reside at the centers of most galaxies. These black holes are not just passive observers, they play a pivotal role in how galaxies merge and evolve over time. But how do they influence these cosmic events? And what happens when two galaxies, each with their own supermassive black hole, collide? The role of supermassive black holes in galaxy mergers. It is like thinking of two galaxies, each with its own supermassive black hole at the center, slowly drifting toward each other across the vastness of space. Over millions or even billions of years, these galaxies begin to interact gravitationally. As they draw closer, their central black holes also begin to feel the pull of each other's gravity. At first, they remain distant, each quietly pulling on the stars and gas around them. But eventually, their mutual attraction becomes too strong to ignore. As these two galaxies collide, their gas clouds begin to mix, and their stars might pass by each other, unscathed by the collision. However, the black holes at their centers experience a much more dramatic interaction. The gravitational forces at play are so intense that the black holes start to spiral toward each other, drawn by their mutual attraction. Over time, these supermassive black holes will gradually lose energy through the emission of gravitational waves, a process known as gravitational radiation. The result is that the two black holes eventually merge into one even larger, supermassive black hole, possibly releasing an incredible amount of energy. This merger would create ripples in space-time that travel outward, detectable by gravitational wave observatories like LIGO. These mergers are not only spectacular in their own right, but they also have important consequences for the galactic environment. The impact on galaxy evolution. Galactic mergers are some of the most dramatic events in the universe. When supermassive black holes collide and merge, they release vast amounts of energy, which can have profound effects on their host galaxies. During a merger, the energy released can be enough to heat gas to extreme temperatures, preventing it from collapsing into new stars. This process is a key component of the feedback mechanism we discussed earlier, where the black hole regulates the rate of star formation in the galaxy. The merger of supermassive black holes can also trigger outflows of gas in the form of relativistic jets, narrow beams of highly energetic particles that travel at nearly the speed of light. These jets are a powerful feedback mechanism. They can blow gas out of the galaxy, halting further star formation and shutting down the galaxy's growth. This leads to what is often called a red and dead galaxy, one that has run out of gas and can no longer form new stars. Interestingly, the final stages of a galaxy merger are crucial for understanding the long-term evolution of the universe. When galaxies merge, the combined black hole becomes even more massive, and the energy released can reshape the galaxy. This process of black hole mergers, galaxy formation, and cosmic evolution is a key area of research for cosmologists today. Gravitational waves. One of the most fascinating aspects of black hole mergers is the release of gravitational waves, ripples in space-time caused by the acceleration of massive objects. The LIGO experiment, and more recently the Virgo and Kagra detectors, have revolutionized our ability to detect these waves and, by extension, study black hole mergers in real time. In 2015, LIGO made the historic first detection of gravitational waves from the merger of two black holes. Since then, more mergers have been detected, revealing the presence of supermassive black holes merging across the universe. But what makes these detections so groundbreaking is the fact that they allow us to study the dynamics of black holes in a way that was previously impossible. Gravitational waves don't just provide evidence of black hole mergers. They give us direct insight into the nature of space-time itself. When two supermassive black holes merge, they release an enormous burst of gravitational radiation, and this energy ripples across the universe. By studying these waves, we can learn about the spin, mass, and even the shape of the resulting black hole. These discoveries are providing a new lens through which we can understand this cosmic dance between black holes and galaxies. The long-term consequences of supermassive black hole mergers are still a subject of intense study. When two black holes merge, they don't just disappear, they form a new, larger black hole. But the surrounding galaxy can also undergo significant changes. As the new supermassive black hole continues to grow, it can influence its galaxy by reigniting its central engine, potentially leading to new periods of active galactic nuclei (AGN) behavior. However, the merger of two supermassive black holes could also lead to a galaxy's death, as we've seen in the case of red and dead galaxies. Over time, the galaxy may exhaust its supply of gas, and the merger process may prevent further star formation, turning the galaxy into a quiet, aging relic of its former self. Interestingly, dark matter and dark energy may also play a role in these events, although their influence is not yet fully understood. As black holes merge and influence their surrounding environments, they interact with the mysterious dark matter that makes up most of the universe's mass. Supermassive black holes and the search for cosmic life. The question of whether life exists elsewhere in the universe has fascinated humanity for millennia. As we venture further into the cosmos, we often look for conditions that could support life, such as liquid water or habitable planets. But could supermassive black holes, objects that are often seen as cosmic monsters, may have a more positive role in the search for life? Could they actually help create the conditions necessary for life? Supermassive black holes and galaxy habitats. While it may seem counterintuitive, supermassive black holes may play an important role in the creation of galactic environments that could potentially support life. How? Well, it turns out that the energy output of active black holes may contribute to the conditions in which stars and planets can form, potentially creating the right environment for life to emerge. In galaxies with active supermassive black holes, the feedback mechanisms we've discussed, such as the heating of surrounding gas or the regulation of star formation, could be crucial in maintaining the stability of a galaxy. For instance, if a supermassive black hole produces enough energy to prevent the galaxy from becoming too hot or chaotic, it may allow for the formation of stars and planetary systems that can support life. Moreover, the heavy elements created during supernova explosions, which are often influenced by the feedback of supermassive black holes, are essential for creating the building blocks of life. These elements, such as carbon and oxygen, are the foundational ingredients for life as we know it. Life near active galactic nuclei? While it might seem unlikely that life could survive near a quasar, the intensely bright and energetic phase of an active supermassive black hole, some research suggests that life could potentially survive in extreme conditions if certain factors are met. For instance, planets located at a certain distance from the central black hole, where radiation levels are manageable, could maintain conditions conducive to life. In fact, astronomers are now exploring the idea that life could exist in galaxies where AGNs are present. These galaxies might have regions that are shielded from the intense radiation by thick gas clouds or magnetic fields, creating an environment where life could potentially evolve. Some even speculate that the energy from an active supermassive black hole could act as a source of power for biological processes in planets or moons within habitable zones. While the idea of life near a supermassive black hole is far-fetched, it's not entirely out of the realm of possibility. Just as life on Earth thrives in extreme environments, from hydrothermal vents at the bottom of the ocean to acidic lakes, life in the universe could potentially find a way to exist under extreme conditions near supermassive black holes. Supermassive black holes and the search for extraterrestrial life. The study of supermassive black holes also intersects with the search for extraterrestrial intelligence, SETI. The enormous energy outputs from quasars, along with the powerful jets and radiation emitted by black holes, have prompted some scientists to wonder whether these phenomena could be used as signaling mechanisms. Could an advanced alien civilization harness the energy of a black hole? Some theorists have proposed that technologically advanced civilizations might be capable of manipulating black holes and harnessing their energy to power intergalactic communication systems or even travel. The role of black holes in cosmic time and the future of life. Looking to the distant future, the role of supermassive black holes in the long-term fate of the universe also presents intriguing possibilities for the survival of life. As black holes continue to grow and merge, they may alter the course of the universe's evolution, influencing the formation of new stars, galaxies, and potentially even habitable planets. The end of the universe. Whether through the collapse of all matter into black holes or the eventual evaporation of black holes via Hawking radiation, raises questions about how life could endure across cosmic timescales. Could life, in some form, persist until the final moments of the universe's existence, adapting to the extreme conditions set by supermassive black holes? The strange and fascinating physics of black hole event horizons. One of the most mysterious and mind-bending aspects of supermassive black holes is their event horizon. This is the boundary beyond which nothing, not even light, can escape the black hole's gravitational grip. But what exactly is the event horizon, and what happens at this point? What we will now explore is the strange physics of black hole event horizons, from the general relativity that governs them to the quantum mysteries that make them such a fascinating topic in modern astrophysics. What is an event horizon? At the heart of every black hole lies the event horizon, the often called the point of no return. This boundary is a crucial feature of black holes, marking the threshold beyond which anything, whether it's matter or light, is doomed to be pulled into the black hole's depths. The event horizon is not a physical surface, but rather a mathematical boundary. It's defined as the point where the escape velocity, the speed required to escape the black hole's gravitational pull, equals the speed of light. Once something crosses the event horizon, no force, not even light itself, can escape. That's why black holes are black, because no light can escape to give us any visual information from inside. Interestingly, the event horizon itself doesn't destroy anything. If you were to fall toward a black hole, you wouldn't be instantly crushed at the event horizon. In fact, depending on the size of the black hole, you might even pass through it without feeling anything too strange, at least at first. It's only as you get closer to the singularity, the infinitely dense point at the black hole's core, that you'd encounter the extreme forces that would rip apart anything that falls in. The warping of space and time. The event horizon is a direct result of space-time curvature, as described by Albert Einstein's theory of general relativity. According to general relativity, massive objects like supermassive black holes warp the fabric of space and time around them. The larger the mass of the black hole, the more extreme this warping becomes. At the event horizon, this warping becomes so intense that it effectively bends space-time itself. It is like space-time as a stretched rubber sheet. Massive objects like black holes cause deep dents in the sheet. The event horizon marks the point where the gravity of the black hole is so strong that, from the perspective of an outside observer, time slows down as you approach it. For someone falling toward the black hole, however, time would seem normal for them, but to an outside observer, they would appear to slow down as they near the event horizon, eventually appearing to freeze in place. This gravitational time dilation is one of the most bizarre consequences of black hole physics. Time itself behaves differently inside and outside the event horizon, and this has profound implications for how we understand the flow of time in extreme environments. Quantum mechanics and the information paradox. General relativity does a great job explaining how black holes behave on a massive cosmic scale. But when we zoom in, way in, to the tiniest building blocks of reality, that picture starts to crack. That's where quantum mechanics steps in, and things get weird. At the heart of this weirdness is one of the biggest puzzles in modern physics, the black hole information paradox. Quantum mechanics has a strict rule. Information can never truly disappear. No matter what happens, the details of a system should always be preserved. But black holes seem to break that rule. When matter falls past the event horizon, it's gone forever. So the obvious question is, where does the information go? In the 1970s, Stephen Hawking made things even more intriguing. As he showed that black holes aren't completely black, they slowly leak energy in the form of Hawking radiation, causing them to lose mass and eventually evaporate entirely. And that's when the real problem hits. If a black hole disappears, and nothing ever escaped from inside it, then all the information about what fell in should vanish too. But quantum mechanics says that's impossible. So we're left with a contradiction at the very foundation of physics. On one side, general relativity tells us the event horizon seals everything in. On the other, quantum mechanics refuses to accept that information can be destroyed. This clash isn't just a technical detail, it's a sign that our understanding of reality is incomplete. Solving the black hole information paradox could reveal a deeper theory that unites gravity and quantum physics. That's why physicists are still chasing it today, because somewhere inside this paradox may be the key to how the universe really works. Theoretical insights into black hole evaporation. One of the most fascinating predictions of quantum mechanics and black holes is Hawking radiation. In 1974, Stephen Hawking proposed that black holes could emit radiation due to quantum effects near the event horizon. This radiation is caused by quantum fluctuations that occur near the event horizon, where virtual particle pairs pop into and out of existence. In this process, one of the particles in the pair falls into the black hole, while the other escapes into space. This emission of radiation results in the gradual loss of mass from the black hole, causing it to slowly evaporate over time. This would mean that black holes aren't truly eternal. Instead, they lose mass over time and eventually disappear, leaving behind only their radiation. The idea of black holes evaporating through Hawking radiation has profound implications for our understanding of the ultimate fate of black holes. It suggests that, given enough time, even the most massive, supermassive black holes could eventually evaporate completely, although this process would take far longer than the current age of the universe. Observing the event horizon. One of the most exciting recent developments in black hole research was the direct imaging of a black hole's event horizon. In 2019, the Event Horizon Telescope (EHT) collaboration revealed the first ever image of a black hole's shadow at the center of the galaxy M87. This historic image was a groundbreaking achievement in astrophysics, as it provided us with a visual confirmation of the event horizon, something that had been theorized but never seen. The image showed a glowing ring of gas surrounding a dark region, the shadow of the black hole's event horizon. This was not the black hole itself, but rather the region where light and matter can no longer escape. By studying this shadow, scientists can learn more about the structure of black holes, their spin, and the nature of space-time around them. In the coming years, with advancements in telescope technology and more data from the EHT, we're likely to gain even more detailed insights into the event horizon and how black holes warp space-time. Black holes and the cosmic microwave background. The universe we live in today is vastly different from the early universe that existed just moments after the Big Bang. But despite the billions of years that have passed, the cosmic microwave background, CMB, the faint afterglow of the Big Bang, still holds crucial information about the universe's infancy. But how do supermassive black holes play into this story? How do they influence the early universe? And what can they tell us about cosmic evolution? The cosmic microwave background, a snapshot of the early universe. To understand the connection between black holes and the CMB, we need to first understand what the CMB is. The CMB is the remnant radiation left over from the Big Bang, and it provides a detailed snapshot of the universe when it was just 380,000 years old. This radiation is incredibly important because it carries information about the conditions of the early universe, including the distribution of matter, temperature fluctuations, and the large-scale structure of the cosmos. In the first few moments after the Big Bang, the universe was a hot, dense soup of particles, photons, and radiation. As the universe expanded and cooled, it eventually reached a point where atoms could form and photons could travel freely. These photons, the CMB, have been traveling through space ever since, carrying with them a record of the early universe, supermassive black holes, and early universe evolution. Now you might wonder, what do supermassive black holes have to do with the CMB? It turns out that these early supermassive black holes may have played a key role in shaping the universe's large-scale structure. While black holes didn't form immediately after the Big Bang, they began to form relatively soon after, as gas clouds collapsed and began to accumulate mass. These early black holes could have influenced the distribution of matter in the universe, helping to shape the growth of galaxies and the cosmic structure we observe today. As supermassive black holes began to grow, they could have affected the temperature fluctuations we see in the CMB. These fluctuations, which appear as tiny variations in the temperature of the radiation across the sky, carry information about how matter was distributed throughout the universe. Early black holes, as well as the energy they emitted, might have left their mark on these fluctuations, providing us with a window into the universe's evolution. The role of supermassive black holes in reionization. One of the most important periods in the history of the universe is the epoch of reionization, which occurred roughly 500 million years after the Big Bang. During this time, the universe transitioned from being opaque and filled with neutral hydrogen gas to being transparent, as light could travel freely across space. This dramatic change occurred as the first stars and galaxies formed and began to emit enough radiation to ionize the hydrogen gas. Supermassive black holes may have played a crucial role in this process. As black holes began to grow and power active galactic nuclei, AGNs, they emitted enormous amounts of energy in the form of X-rays and ultraviolet radiation. This radiation likely helped to ionize the gas in the early universe, contributing to the reionization of the cosmos. The feedback from black holes may have been responsible for heating up the gas surrounding the first galaxies, allowing the universe to evolve from a cold, neutral state to the more transparent and ionized state we see today. The influence of supermassive black holes on large-scale structure. In addition to influencing the CMB and reionization, supermassive black holes may have played a role in the large-scale structure of the universe. The distribution of galaxies and the formation of cosmic filaments and voids are directly influenced by the distribution of dark matter and the energy produced by supermassive black holes. As black holes grew, they could have affected the motion of gas and matter, creating the structures we see today. By studying the CMB, astronomers can trace the influence of these black holes back to the early universe and better understand how the universe evolved over billions of years. A new frontier in cosmic exploration. The study of the CMB and the early universe is still in its early stages, and advancements in technology, such as the James Webb Space Telescope and the next-generation CMB experiments, will provide new insights into the role of supermassive black holes in shaping the cosmos. By studying the cosmic microwave background, we can unlock the secrets of the universe's infancy and gain a deeper understanding of how black holes have shaped the structure of the universe. Black hole mergers and the cosmic symphony of gravitational waves. The universe, as vast and mysterious as it is, can often seem like a giant cosmic orchestra. Every event in space, every collision, explosion, and movement produces ripples that spread across the fabric of space and time itself. Some of these ripples are so faint and distant that they're almost imperceptible, while others are so intense they shake the very foundation of the cosmos. One of the most remarkable sources of these ripples are black hole mergers. When two black holes collide, merging into a single, larger one, and releasing an enormous burst of energy in the form of gravitational waves. These waves travel across the universe, carrying with them the story of one of the most extreme events in the cosmos. But how do these waves work, and what do they tell us about the universe? To understand how black hole mergers and gravitational waves come together, we need to start with the fundamental idea of gravitational waves themselves, an idea that had been theorized by Albert Einstein over a century ago, but only recently confirmed with groundbreaking experiments. These waves are ripples in the fabric of space-time, caused by the movement of massive objects like black holes. In simple terms, as objects like black holes move, they create distortions in the fabric of space-time. Much like dropping a stone in a pond creates ripples across the water's surface. Gravitational waves travel outward, spreading their energy across space at the speed of light, carrying information about the objects that created them. The fascinating part? These waves are incredibly weak, making them challenging to detect, but their power lies in the ability to capture details about the most extreme cosmic events. For many years, gravitational waves were simply a theoretical prediction, something that existed only in equations and thought experiments. But in 2015, scientists working with the Laser Interferometer Gravitational Wave Observatory, LIGO, made a historic discovery. They detected gravitational waves for the very first time. The waves came from a black hole merger, and the event marked a new era in astronomy. It was as if the universe had just played its first note in a cosmic symphony, and the world was listening. The black hole merger that LIGO observed in 2015 occurred when two black holes of about 36 and 29 times the mass of the Sun spiraled toward each other over millions of years. As they got closer, their gravitational pull became stronger, pulling them ever inward in a deadly dance. Eventually, they could no longer resist the pull of their mutual gravity. They collided, merging into a larger black hole, and in that final moment of cosmic chaos, they released an incredible amount of energy. The result? A burst of gravitational waves that LIGO was able to detect. This was the first ever chirp, as scientists call it, of a black hole merger, where a sharp increase in frequency and amplitude of the gravitational waves as the black holes merged into one. Gravitational waves are not just a simple signal. They come with intricate patterns that can reveal profound details about their source. As black holes spiral toward each other, the frequency of the gravitational waves they produce increases, and the signal itself becomes stronger. Imagine listening to the sound of the universe, a chirp that rises in pitch as two objects draw closer together, only to peak in a burst of energy as they collide. It's not just a noise, it's a symphony that tells us about the mass, spin, and behavior of these black holes as they merge. This chirp has become an iconic signature of black hole mergers. The frequency and strength of the waves are like fingerprints, unique to each black hole merger. By analyzing these signals, scientists can extract a tremendous amount of information. They can determine the mass of the black holes before the merger, how fast they were spinning, and even how far away the event took place. The gravitational waves from this event provided us with a snapshot of black hole behavior in the final, most intense moments before their merger. And that moment of collision is just the beginning. In the aftermath of the merger, the resulting black hole isn't left in a peaceful state. Instead, it goes through a phase known as ring down. The black hole that forms from the merger is initially highly distorted, and it sends out further gravitational waves as it settles into a stable state. These waves, much like the ringing of a bell after it has been struck, carry detailed information about the properties of the final black hole. The shape and intensity of these ringing waves can reveal details about the black hole's mass and spin, providing insights into the physics of black holes that were previously hidden from our view. Gravitational waves themselves are incredibly weak by the time they reach Earth, which is why detecting them requires such precise technology. LIGO works by using laser interferometry, a technique that measures incredibly small changes in distance on the scale of about 1/10,000th of the diameter of a proton. When a gravitational wave passes through Earth, it causes tiny distortions in the fabric of space-time, which LIGO detects. Despite the challenge, LIGO's success in detecting these ripples has given us an entirely new way to observe the universe, without relying on light. Gravitational waves, unlike light, can travel through dense matter without being blocked or absorbed, making them invaluable tools for studying some of the most extreme and invisible phenomena in space. As more gravitational wave detectors come online, our understanding of black hole mergers will continue to evolve. But this new tool is not just useful for studying black holes. It opens up a whole new field of astronomy called multi-messenger astronomy, where gravitational waves are paired with traditional electromagnetic observations, such as radio, optical, or X-ray signals. In 2017, for instance, scientists detected gravitational waves from the merger of two neutron stars and simultaneously observed the electromagnetic signal from the event, a gamma-ray burst, giving astronomers new insights into the formation of heavy elements like gold and platinum. This dual detection approach promises to revolutionize our understanding of not just black holes, but all types of cosmic phenomena. The detection of gravitational waves also provides new insight into the birth and growth of black holes. Before we had this technology, much of what we knew about black holes came from indirect evidence, such as the movement of stars around unseen objects. Gravitational waves allow us to observe black hole dynamics directly, giving us a clearer picture of their formation and evolution. Every black hole merger observed by LIGO adds a new piece to the puzzle of how these massive objects form and interact over time. What makes black hole mergers so exciting is that they take us to the extremes of physics. These collisions occur in some of the most extreme conditions possible, where the laws of physics are stretched to their limits. The study of gravitational waves from these events allows us to test general relativity in ways we never could before. For instance, scientists are using these waves to test whether Einstein's theory of gravity holds up under the intense conditions near black holes. So far, the data has matched the predictions made by general relativity. But as more mergers are observed, we might find new deviations that could point to new physics. The mergers of black holes also give us a window into the history of the universe. Since gravitational waves travel at the speed of light, They carry information from across vast distances. When LIGO detects a signal, it often comes from a black hole merger that happened billions of years ago, providing a glimpse into the early history of the universe. This long-distance, time-traveling aspect of gravitational waves means that each detection is a snapshot of the cosmos at a different point in its evolution, allowing us to study cosmological events that would otherwise remain hidden. Perhaps one of the most fascinating aspects of black hole mergers is the information paradox. According to quantum mechanics, information about a system should never be lost. But the very nature of black holes suggests that anything that crosses the event horizon is forever hidden. The detection of gravitational waves may offer new clues to resolving this paradox. When two black holes merge, we can't observe the information that's lost inside the event horizon, but the waves they emit before and after the merger carry subtle clues about their internal dynamics. Understanding these signals may eventually provide answers to some of the deepest questions in physics. In the coming years, next-generation detectors and space-based observatories like LISA will further enhance our ability to study black hole mergers. These detectors will be able to detect supermassive black hole mergers and provide even more precise data on the dynamics of black hole systems. As we continue to probe the universe using gravitational waves, we are opening a new chapter in our understanding of the cosmos, one where the invisible becomes detectable, and the most extreme objects in space reveal their secrets. Gravitational waves from black hole mergers have ushered in a new era of cosmic discovery. These waves, which carry the sound of black holes colliding across the universe, are changing the way we understand space-time, the evolution of galaxies, and the nature of the most extreme environments in the universe. Every gravitational wave detection is like a note in the universe's symphony, adding a new layer to our understanding of the cosmos and opening the door to new scientific frontiers. Supermassive black holes are often described as the universe's ultimate monsters, dark and endlessly consuming. But the deeper we look, the clearer it becomes that this image is incomplete. These objects are not just destructive forces hiding at the centers of galaxies. They are organizers, regulators, and, in many ways, quiet architects of the cosmic structures we see today. At the heart of nearly every large galaxy, including our own Milky Way, sits a supermassive black hole. Despite being incredibly small compared to the galaxy around it, its influence is enormous. Through powerful jets, intense radiation, and gravitational dominance, it shapes how gas moves, when stars are born, and even when star formation must come to an end. Galaxies do not simply evolve on their own. They evolve with their central black holes, locked in a long and complex relationship. This connection tells us something profound. The universe is not chaotic in the way we once imagined. It is regulated. When galaxies grow too fast, black holes push back. When gas piles up in galactic cores, black holes heat it, scatter it, or eject it entirely. In doing so, they prevent runaway star formation and help galaxies settle into stable, long-lived structures. Without this regulation, the universe might look radically different, either overcrowded with stars or unable to sustain them at all. What makes supermassive black holes especially fascinating is that their influence extends far beyond their immediate surroundings. Their feedback can reshape entire galaxies across millions of light years, altering the fate of billions of stars. And yet, despite their importance, much about them remains unknown. How did they grow so massive so quickly in the early universe? How exactly does information behave at their boundaries? And what do they reveal about the deeper laws of reality that connect gravity and quantum mechanics. These unanswered questions are not signs of failure. They are invitations. They remind us that science is not a finished story, but an unfolding one. Every observation, every simulation, and every new theory brings us closer to understanding not just black holes, but the universe itself. So, the next time you look up at the night sky, consider this. The calm glow of distant galaxies is shaped by forces we cannot see, anchored by objects that bend space, time, and matter itself. Supermassive black holes are not just symbols of cosmic destruction. They are essential characters in the universe's ongoing evolution. Silent, invisible, and unimaginably powerful, they continue to shape the cosmos and our understanding of it in ways we are only beginning to grasp. If you want to keep exploring the hidden forces that shape our universe, subscribe and join us as we uncover the stories written in the stars.